Okay, so topic for today is the Stinespring dilation theorem. So I briefly stated it at the end of the last lecture, so let me just repeat that. So we're looking at a map. So this is a completely commutative map from the C-star algebra So then, given these objects, I'll make a comment about C-star algebras in a second, right? So for the moment, for A, just think of the bounded operators on the output Hilbert space. Right? That's the standard situation that we look at later. And I'll do this a little bit more generally because actually that's natural in the course of the proof of the theorem, as you will see. So given such a completely positive map, there are three objects which together represent that. A Hilbert space, called H hat. Now there always is a Hilbert space, right? But the second bit is a star representation. Call that pi. That's also a map into B of H. So it's sort of an object of the same kind, only to this other Hilbert space. So, and three, a bounded operator. B from H to H hat. So all this says nothing, right? Of course, the representation formula carries the information, so that T of x is always V star I of x. So just to check the syntax, right? V is an operator from H to H hat. So this V takes me to H hat. Pi of x for any operator in A is an operator on H hat. So that acts on this vector that we get here. And then V star is a map back to H. So the whole thing goes from H to H. And that's what we want, because T of x is an element of B of H. Right? So this is the sort of syntax check that you should always do when you see formulas like that. Okay, so these objects are unique. On an earlier occasion I said essentially unique, and that's what I mean here. Right? So there is an obvious way to rename everything in H hat so that you get another Hilbert space, which is just a unitary image of H hat. It's basically the same space for all in all ways that are relevant for us. And that gives another representation, and I just follow this up with a map to another Hilbert space maybe, and then this formula will be true again, right? By just unitarily transforming H hat to another space. And that's the kind of uniqueness that is actually part of the theorem. Right? So these objects are unique, provided that So this is a set of vectors, pi of A, V, phi in H, A in A. And let me just say spans H hat. Right? Clearly this is a subset of H hat. And the statement is that the linear hull of that space, this is not necessarily a linear subspace, but the statement is the linear hull of that space, all linear combinations from this, of vectors of this kind, that will be a space which is dense in H hat. Right? That's the kind of uniqueness that we also had in the Kolmogorov dilation theorem, which is, after all, basically, I mean, this is a special case. Okay, so the proof, and there will be further parts of that theorem, but for the moment I split that up a little bit, and first just prove the dilation form. So proof goes via the Kolmogorov dilation. And there is, as always, in order to apply that theorem, there's going to be a positive definite kernel, and then we use the kernel construction from Kolmogorov. So via Kolmogorov dilation of the kernel, now comes the kernel. And let me just write it already in the form of the Kolmogorov dilation, that is, our set on which this kernel lives is the set of pairs of an algebra element and a state. Right? And so we had a map V of X that would give us a vector for every element in that set, and now for every pair we get a vector. Right? This is going to be the space H hat. Right? And the essential information that goes into the construction is what are the scalar products of these guys? Right? This is then the positive definite kernel. And there's a simple formula for that in our situation here, which is phi t a star b psi. So this kernel is completely determined by the objects here, by t, right? As you can see. And so the first thing that we have to check in order to apply that theorem, we have to show that this is actually a positive definite kernel. Okay? So how do we do that? So, and actually, my first claim will be is that T is CP, completely positive, if and only if this is a positive kernel. So we see that the condition of complete positivity is essential here. Actually, it's easy to see that every representation is a completely positive map. And also, writing an operator in front and after with a star, we also saw this as a completely positive operation. So it's actually clear that a necessary condition for this kind of representation to hold is that T is completely positive. And the theorem, so the non-trivial part is actually to say that, to prove that it's also sufficient. So there's a converse. If this guy is completely positive, then we can actually find such a representation. Okay, so how do we do that? Well, what do we have to show? We have to show that the norm square of arbitrary linear combinations of these V vectors is positive. And linear combination now just means finite linear combination, right? So we have to show that some I, B of AI, phi I, right? Norm square, whatever that is, but this has to be positive, right? If we write out what the norm square of that vector would be, we have to get a positive number. That's exactly the condition for a positive kernel. Okay, so let's write that out. So this would be a double sum, because of course by definition this is linear, or sesquilinear. So we have sum Vij. Also one thing, I dropped the coefficients here. And the reason being that from the form of this, I could include coefficients, but they wouldn't change much. Let's put them in. Doesn't matter. So we get these coefficients of the linear combination out, and of course we have only finitely many terms in this sum. So you don't have to start worrying about the convergence of anything here. Right? So these are finite sums. And then I have the scalar product of the corresponding elements here. So this is, so I write it immediately in that form, phi I t ai star aj phi j. Now, this is an n by n matrix of operators here. And now n by n matrices of operators we already looked at, because we can think of these as n by n matrices of with entries in our algebra, let's say, over n by n matrices with such entries, right? So call this. So this matrix here actually is identity or T-tensor identity acting on some matrix M and the ij component of that. So we checked that earlier, right? So there is a correspondence between M between matrices with operator entries and operators on a space that has an additional tensor factor Cj. And the way it works, just to remember, is that M is whatever matrix you write there multiplied with the matrix units. Right? So this is actually an element in the C-star algebra here, tensor the D by D matrices over C. Right? So the D by D matrices have this as a basis, and if I have any element in this tensor product, I can expand it in this way. Right? Because I choose a basis in the second factor. These are the matrix units. They are 1 in one place and 0 otherwise. And this is the same as writing an A-valued D by D, N by N matrix. And then we saw if you apply T tensor identity to something like that, this part doesn't change because you have the identity on it. But here everything is mapped with a T. And that's exactly what is happening here. Right? So now T tensor identity for a completely positive map is positive. So this will have something to do with positive matrices going to positive matrices. Now I claim that such a map is positive. Such a matrix is positive. So we check the following fact. Such M is positive. If that is positive, that also, okay, so, and actually I want to say a little bit more. Then all positive matrices are linear combinations of such guys. So, and for that, let me do the fast version of that. The fast version is to introduce an operator A hat, which is the sum of the AI. Now, AI is just an arbitrary collection of operators, right? Finite collection of n operators. and I multiply that with a ket. Now the ket is also a bra, sorry, with a bra. Bra is also an operator, so I consider that as a map from Cn to C, which just takes out the ith component of a vector. And then if I write a hat star a hat, there's a first tensor factor which is a-valued, and a second tensor factor which has operators between complex spaces. Right? They change dimension here, but that doesn't matter for this argument. If I take the product, I get some ij, ai star, tensor the star of this, right, which is that. Oops, some I times some j, aj, tensor j. And I can just multiply that together and get what I have. Now, this form of a matrix should be familiar. If you have a matrix that has, suppose the a's were numbers, and you have a matrix like that, what is a typical property of that matrix? Any idea? If you have a matrix of numbers that you can write like that, so Mij is this. What kind of matrix is that? I can't hear you.
Positive.
It's definitely positive, yes, but we know more actually. So this is actually a ket product in matrix notation, right? So if you actually just write it out like that, or like this, right? So this is actually the ket, or the ket. And now we just do everything operator valued. So this is basically, in numbers, this would be a rank 1 operator. And the AIs are just the components of the vector, for which you take ket bra psi psi. Right? This is actually the corresponding bra, and this is the corresponding ket now. So just take everything operator valued. Right? So we expand in the standard basis, the ket I basis, and the coefficients are now operators rather than numbers. So this is why you can see straight away that this should be positive somehow. And this proves it, but also you could, so the proof of actually checking that this is positive by taking scalar products and sum up is the same as they take the positivity of that. Right?
Wasn't this one of the definitions of positivity?
Sorry?
Wasn't this one of the definitions of positivity that we can say?
Yes.
So.
Yeah. Well, yeah, but let's connect it to the definitions of positivity here. Right? So, is every operator of this form, right? I said here, such M is positive, are all positive operators such. Can they be written in this form? Well, no, right? Because not every positive operator is rank 1. But the sum of such guys should do. Well, that's actually true, because so an arbitrary is a sum of these guys, sum of such rank 1 elements. How is that? Well, very simple. We have a choice of definitions of positivity. Actually, M positive means that M is something like B star B. Right? That was one of the definitions of positivity. So Mij is then B star, well, yeah, B star space, sum over K, B star, I, K, B, K, J. That's just a matrix product, and the adjoint, well, I haven't plugged in the adjoint yet. Right? The adjoint actually means that this is the sum over K, B, K, I, star. This is tricky stuff, and you can make mistakes. Now B star is the adjoint of the element B in the larger space. I mean, with a tensor factor, and this connects it with the star in the algebra, one level lower somehow. Right? So these are kind of different stars. This is something that applies to every matrix element, and this is the element that applies to the whole matrix. Right? So if you just think of K as a parameter running from 1 to n, then this is exactly of the form that we've written, right? So this is like something I, take the adjoint, times the same something J. So this is exactly an operator of this form. And it's, you just need K terms. It doesn't matter what the dimension of the matrices in A could be. You don't even have to think about that. This is actually an advantage of this slightly more abstract version of the Stinespring dilation, where we just use the algebra use a map starting from an algebra. I think I promised some remarks about C-star algebras. I'll postpone that. Let's just continue with the argument. So now we know that this is a positive, that this is a T tensor it on M. M is positive, right? That's this matrix, this element. So T tensor M on that is also positive. That is the condition of complete positivity. So, but that means that T of AI star AJ is a sum over K of some B, what did I write there? B-I-K, B-K-I, B-K-I. So this scalar product is equal to the sum over I and J, Ci bar Cj, and then to star that over to the other side, there's also a sum over K, Bki phi I Bkj phi j, and so this is just the norm squared of some vector phi, and this vector phi we can read off here as being the sum on j. We can't do anything about that sum, but these terms are all positive. Right? So phi k is actually sum Cj Bkj phi j. Right? So that depends on k, but that's okay. Each one of them gives a positive contribution to the sum, so this is positive. So this is the positivity of that kernel, and I think you see in this computation that the opposite will also be true. I already said it's anyhow obvious that complete positivity is a necessary condition for that kind of representation. So it has to come out, so it has to be equivalent, right? Just looking at the overall theorem. But you can also see it in detail, because what you really need is, if you have it for these sort of rank 1 operators, you have it for all anyhow, that you get a positive matrix out of that. And that's also goes in the other direction. Okay, so we can just apply the Kolmogorov dilation. And so how do the other objects that are written here? So actually, so we have V of A phi would be vectors in H hat, right? They are guaranteed. The existence of such vectors is guaranteed by Kolmogorov. And now let us just define V phi, where phi is in H. Right? This is the representation space of the image. Is just V of the identity of phi. There is a subtlety here because in the general C-star algebraic business you don't have to have an identity and then you have to work a little bit to get it back in. But our C-star algebras have identities, so we don't really even think about that. And the representation is defined on these starting vectors, right? So the linear combination of these guys spans the whole space H hat. And I claim that there is a unique for every A, there is a unique operator which maps this vector into VAB phi. Now there's a few things to prove here, right? This part is just a straightforward definition. But of course, this if we collect the two together, then we would have that V of V of A and phi is indeed just phi of A V phi, and those are the vectors that we talked about, right? that are mentioned in the statement of the theorem. But what we do have to work on is to establish the existence of these operators on H hat. Right? Is that a well-defined operator? Well, what could go wrong? Or what do we have to establish in order to make that conclusion? Now, there are several things that could go. Yeah?
One question, are these all the same V's or different V's?
The V's, there's a lowercase v, which has two arguments, namely A and phi. And there's one operator with a capital V. Is that okay? One shouldn't do things like that, I admit that. But okay. So what could go wrong here? Right? So we define an operator on some basis elements. Now these basis elements are not orthogonal or anything. They're not independent. So it is actually possible that different linear combinations are the same in H hat. Right? So these vectors are linearly dependent, which makes it problematic to just define an operator like that. Right? So if we had guaranteed that every vector has a unique representation in terms of these guys, then of course I can just define the operator by this. But I don't know that. Right? Actually, it's false. So the thing to do is establish in the same step first, if I have a linear combination of such operators, let's say bi, phi I, and this is 0, right? Because we have found a linear dependency. Then it must follow that pi of A on this vector is also 0. Otherwise, it's not even an operator. Okay? So this would be that the operator is well defined. That still doesn't quite, there's no contradictory images that you can compute with that, right? With this formula. That's one step. 2, this has an extension by continuity. So, of course, our Hilberts, we want to define an operator that is defined in all of H hat. So, it's not enough to define it for arbitrary linear combination of these spanning vectors. I could have a vector that is a limit of these guys. And that should also give us a good value for the image, right? Now, the way to do this in a single step is to show that the norm of pi of a sum, and I make scare quotes in here, CV of b I phi I. So I take what my formula says the image should be, right? And that is some sum that we can compute, and I will compute its norm squared. That I can do in a straightforward way. And I would like to show that this is less than actually the constant here is norm a squared times the norm of this guy. So the linear combination vector that I'm testing on. And in all cases, we look at finite sums here. Right? Okay, so why does that do both steps at the same time? So this I can write down actually. What I mean by this funny notation is that I look at the vector sum I ci v of a bi phi I. So I take the modification that my operator is supposed to do in the end, and now this is a well-defined sum in my Hilbert space, right? I can just compute this side if I have all the data, right? And the claim is that what I get out of this actually satisfies this bound. Now this solves problem number one. Sorry, I moved it away. Problem number one says that if this is the zero vector, then my image should also be zero. But that's exactly what this says, then 0 is less than 0. So it automatically takes care of this injectivity. And it also says that this densely defined operator is actually bounded by this number, and therefore has a continuous extension. So Cauchy sequences get mapped to Cauchy sequences, and therefore any convergent sequence is mapped to a Cauchy sequence which has a limit, and that's what we define as the limit. So this is what is called the extension by continuity. Right? So I have to show that this is continuous in the norm, right? Which is the same as saying it's bounded. And so how do we get this? Huh? Okay, so of course this notation is not legitimate, not allowed before I actually establish that this inequality holds. Right? So, but it tells you what to prove, and this is why I sometimes use these quotes here. Right? What wants to become that expression can be written down with what wants to become the definition. Then I do the estimate, and from that it's clear that there's a well-defined element that depends continuously on the vector, and therefore it's a linear operator. Okay, so how do we get? We have to look at these scalar products, and other way. Okay, so what is this? Again, we have the sum ci bar cj. There's also another. I could have put in a step number 3 there. Right? I wrote down the formula. The claim here is that this is a linear operator, and also that this is a linear operator. So I did that automatically by evaluating it on arbitrary linear combinations of these vectors, and that the definition is such that you can pull out these linear combinations. Right? So it's automatically linear. Right? So that's another side remark. So this formula defines something, some vector on that side maybe, but we want to show that this is actually a bounded linear operator. So, but this comes from saying that I check this on arbitrary linear combinations, and actually this will be linear in A, and so on. So we had an example of this before. When you look at this VB phi definition, and your kernel, as written here, is linear in phi and linear in psi, then automatically this is going to be linear in phi and psi. Right? We checked this because there's a norm squared difference that you can look at that gives you this identity for free. Right? So in this whole dilation business, things like that are actually automatic. Right? And the same is the linearity in A, because this is linear, conjugate linear in A and linear in B, and automatically this is going to be, this whole expression will depend linearly on A. And, but again, this is also covered in the bound that we are about to prove. Okay, so here we go. This is, I have to look at the scalar products of these guys. So this is T of B, well, A, B, I star, which is B, I star, A star. Then there's BJ and apology. So again, we have here, we want to show that this is positive and actually, well, this is automatically positive because these operators A, B, J are, we checked that already, right? This is a sum of norm squares, so it has to be positive anyhow. So there are different ways of doing that. One possibility would be to look at another operator, A prime, so that A prime star A prime is 1 minus, or let's say, norm A squared 1 minus A star A. Right. This is a positive operator. A star A has maximum eigenvalue, or maximum top of the spectrum is the norm A squared. So this is a positive operator. It has a square root, right? So I apply this whole thing to this operator, find that that must be a positive scalar product, and that's one way to prove this formula, right? The other way to prove it is to go back to this is a bit indirect. And in the end, everything is of course equivalent, but another way to do that is to look again at this operator B hat, which is some Bj tensor bra J. And then we look at, so this operator, so the sum of B I star A star A B J, right? So this is a matrix of operators, and so if I just want to look at the corresponding element, I just add the K-bras, right? And then this is equal to the sum over I and J, or the sum. I have the sum already, right? So this is B hat star A star A B hat. No sum. Okay. if I write out the sum, you'll just see that the i's and j's collect here, and the a star a is in the b parts. Right? Do it more explicitly. Is okay? So, but now I know that a star a is less than a squared times the identity. Right? And this is a positive map. So this is b hat star norm a squared identity tensor identity. Well, that's just a number. So this is equal to norm a squared b hat star b hat. And because t is completely positive, you can do this estimate under t. Right? So this is so if you apply t to every element here, then you have the same estimate. And if you put that together, you just get this constant out, and the rest is indeed just the norm of the vector. Okay, so that is well defined on h hat with bound and the norm of pi of a is less than the norm of a. Right? So just take the square root of that. When the norm of pi a squared is less than a small a squared. So also, if I look at pi of a b, b of c phi, this is pi of a, well, this is v of a b c phi. But bc is just another operator, so this is pi of a v bc phi. And then I can pull this one out again, so this is pi of a pi of b v of c phi for arbitrary vectors of this form. So because these span everything in the minimal version, we see that this is a representation. This is simply bookkeeping and seeing that if you have a definition like that, then automatically it produces a representation. And also pi of a star pi of a star. For that you simply have to take out and look at a scale product and do the same thing. So this is a star representation. And so basically, yes, I think this finishes the sketch of proof for this. For the whole theorem. So why, just a few comments. So one comment is why this if you want fake generality, putting a C-star algebra in it. Actually, we're not going to work with arbitrary C-star algebras. But when you see how the proof goes, all you need about the source of T, or the space on which T acts, is this algebraic structure. And therefore it's actually no problem to just include this generality. Everywhere in the proof we have these A-valued matrices and so on. So just sticking to A-valuedness of various things makes the proof relatively smooth. Otherwise you have to think of these as explicit operators. And this then also immediately contains the Naimark dilation, because in that case, the output space is simply an abelian algebra. That is the continuous function on a measure space, let's say, with the topology, or maybe just measurable functions also works. Right? So then, okay, so let's see how the Naimark dilation fits in there. I think I need some space. Anybody know who the responsible Hausmeister is for that thing? So let's treat that as an example. So the conditions for that special case is that the output is classical. So A is commutative. So now an observable can be seen as a map that takes A to B of H. H would now be the system Hilbert space. And what does this do? This would take, so T of, let's say, so this means it's isomorphic to the set of continuous functions of some set, some compact space. So this in the example that we made for this Naimark dilation, X was a finite set actually, and so when we have F sub X, right? So there are these positive operators for the individual outcomes, and this map here has to be a positive map, and you can also check it's completely positive. And well, that defines the observable basically. Now, the dilation process produces something out of this where at this end we don't have just a completely positive map into B of H, but into representation into the larger space. Right? So pi from H to B of H is a similar beast. So it's also observable. But it has this product property. So with pi of Fg equal to pi of F pi of G. And if you look at what this means, because F and G are basically arbitrary, then let's say something like that, right? So I just wrote the product of the functions as the same thing with different arguments, but with a delta function. So that this is actually f of x, g of x, and this is what the observable gives you for the product. And on the other side, I just do the sum separately, and I get twice the same thing. So this has to be 0 for all of f and g. But that just means that this bracket has to be 0. Right? So which is just the definition, the condition for projection values. Right? Because if you take x equal to y, it says that this has to be a projection, and if x is different from y, they are orthogonal, so they multiply to 0. Right? So the homomorphism property here of the star representation is actually the same as saying that you have a projection value measure. And well, if you just put it together, this makes it clear that Naimark is actually a special case of Stinespring. The other extreme special case, which is something that one of the first things that you learn about when you go to a lecture on C-star algebras. Now, this is my short comment on C-star algebras. C-star algebras are algebras of operators, essentially, or you have a vector space, that you have a product, and so on, and the rules for manipulating these, for the algebraic rules for this algebra, for this abstract algebra, are directly taken over from operators. So actually every C-star algebra is isomorphic to an algebra of bounded operators, with all the structures where the star actually means the adjoint, and the product is the product of operators, and so on, and the norm is the norm of the operator. So basically this is, so the T here, when I say go to a C-star algebra, T could be defined on a subalgebra of the operators, and the theorem would still work. So this is what helps. And one special case in this context is, and this was actually for a long time an open problem in the theory of operator algebras. So if you take these axioms that you read off from the operator world, and you postulate them for an abstract algebraic structure, can you show that actually these guys are all isomorphic to operators in Hilbert spaces? This is a claim I just made. Right? But this was in the early days of C-star algebra theory. This was one of the key open problems, to check whether all the structure that had been extracted from the operator case, if you turn that into axioms of your algebraic structure, whether that is sufficient to give you something that will be, in the end, isomorphic to an operator algebra. And one of the key steps in this was the so-called GNS representation, where out of an abstract algebra, and the only thing we used here in the Stinespring dilation was this abstract algebraic structure, right? Operators of which you can take a star and that you can multiply, and such that A star A is positive. Right? Or actually, this is the definition of the positive cone in a C-star algebra. So how do you get from this abstract world of C-star algebras into the world of operators? Well, this is it. Right? So you take, if you have another example, but this is very short. So then H is one-dimensional. And this is the GNS representation. So then actually T then, if the algebra, or if B of H, so we just, I should say this is Gelfand, Naimark, Siegel. My transliteration of the Russian is not very good. There should be some soft sign here and a funny eye sign. I don't know. So anyway, so this is a construction that served the following purpose: start from an abstract C-star algebra, and T of A to B of H is positive. It's completely positive, actually, we need. But for states, this turns out to be the same thing. Right? So this is C, B of H is then also C. So this is a linear functional, and that is positive. And these guys are just called states. So suppose I have a positive linear functional on a C-star algebra, then the Stinespring dilation gives me an Hilbert space, and what else? A Hilbert space and a representation. It tells me how to get operators out of this. Right? So get representation So, conclusion. C-star algebras are the same as norm-closed subalgebras. Of star subalgebras of operators. So the star subalgebras just means that with A star is also an element of the algebra. If you don't postulate, you get that. You get a more general structure called Banach algebras, and they have C-star algebras are in many ways the easy part of the Banach algebra theory. Okay, so also, so the GNS representation. There's something that in quantum information theory is usually called the purification construction. And we'll come to that at some point. Okay, but let us continue with the Stinespring theory. So because we've still to mention one important part of this whole dilation construction, namely the comparison theorem. So get T from A to B of H, same setting, TCP. With minimal dilation. Minimal is this unique thing, right? Minimal dilation H hat B phi, these objects. Okay, so suppose, and so this is one thing. Now we want to compare two such elements in the CP ordering. Right? So there's another cone here, the cone of completely positive maps. And we want to characterize the intervals in that set. So that's T1 from A to B of H. That's another guy. The linear with T1 and T minus T1 CP. So you could say that if I write, let's say, if this means that TCP, if I introduce this kind of notation for completely positive, then what I wrote in it is that we have something that is squeezed in between 0 and t. Right? Because the second inequality just means that t minus t1 is CP. Right? So I split a given t into a sum of positive ones. This is a very important operation because it has something to do with the classical information that I can obtain while t is in operation, or while t is applied. So the consequence is then is unique Now this lies between 0 and 1. And actually if it's equal to 1, then t is equal to t1. Such that this f1 commutes with the representation. So that's just one condition. But why is it useful? T1, I'll just pull this down in a second. T1 of x is v star pi of x. So this begins like the Stinespring representation of t, but now I put this operator in here. Now, suppose I'd forget about this condition and just write a formula like that. This would, whatever f1 is, it will define some kind of a map from A to B of h hat, to B of h. So, so what is this commutation condition for? Well, if f1 and pi of x don't commute, then you can immediately see, oh, let's say f is only, f is maybe positive, but it doesn't commute with this pi of x. Then if I take the adjoint of this equation, then I get something different from t applied to x adjoint. Right? So this has to commute in order for to guarantee that this can take Hermitian elements into Hermitian elements. Right? So this is a sort of a minimal requirement. And actually, if it does commute, then these operators also commute with the square root of f1. So I can pull this over and I immediately see that this is completely positive. And if I apply that with the square root of 1 minus f1, then I see that this is also, that t minus t1 is also completely positive. Right? So, okay, so these conditions on f1 are clearly sort of necessary. Now let's see that they're sufficient. So T1 has a dilation of its own. Oops. So this would be, I put a 1 everywhere here. Right? Just these three objects. So define an operator W from h hat to h1 hat. And I do this by just taking over the corresponding scalar product, so that actually W of V of A phi, these defining vectors, so to speak, would be the V1 A phi, which is, of course, pi 1 of A V1 phi. Right? So this would be in the Hilbert space h hat 1. So this is an operator, period operator from h hat to h hat 1. And we have the same problems as before. We have to check that this is well defined, that this is actually a bounded operator, and so on. Right? So what do we have to check here? That the norm of this linear combination, right? Ci pi 1 a v1 phi is less than or equal to the corresponding thing without the ones. So I write out everything here in terms of Wait a minute, I should have I. So these are just the standard linear combinations that we use for the dilation construction. And this is the sort of thing that we have to show. But this is equivalent to saying that the sum ij, ci bar cj, phi I. Now on this side, I would just get that this scalar product is given by t of ai star aj, and here I get t1. I subtract that onto the same side. Okay, so the difference of these two, the two sides of this inequality are just that. Now, t minus t1 is defined exactly like that, and it's supposed to be completely positive. So therefore, this expression is going to be positive. Right? So this is this inequality actually follows from this little computation here. Right? So comparison is easy. If I do know that the difference is actually also completely positive, then I can immediately bound that sort of scalar product, this sort of scalar product, in terms of that sort of scalar product. That's the whole idea of the Stinespring dilation. So this means that, so it follows that W is well defined. With norm W less than 1. So this allows us to just get the representation, to connect the two representation formulas. So T1. We have to get a few more relations here. Now, first of all, if that is the definition, so W V of A phi is V1 A phi. So this implies, in particular, if I pull out an additional factor, I get that W pi of A is pi 1 of A W. Because both I get by pulling out a factor A out of this first argument, so there could be an AB here, and then the whole thing acts on an arbitrary vector. This is where we need the minimality. And so this is called an intertwining operator between these two representations. And also W of V phi, which is just the same thing with A equal 1, gives the same thing with A equal 1 on the other side. So this is V1. Right? So therefore, I get T1 of X is equal to, of course, V1 star pi 1 of A. V1, that's just the Stinespring dilation of T1, of the smaller guy. So I can just plug in these values. So this is V times star W star, that is just this V1 star. Then I have the pi 1 of what is it? A or X, whatever. A, and the V1 again becomes a W V. But now I use this intertwining condition, so I can just pull this through, or maybe the other direction. Right? So this is V star pi of A, W star W V, so we said F1 is W star W. So this is the comparison theorem. I sometimes call that a Rado-Nikodym theorem, because Rado-Nikodym has to compares two measures. Here we compare two positive maps, and there is something like a density, which would be the F1. It's not exactly the same, so I tend to avoid that these days, but comparison theorem actually describes it quite nicely. So this will be a very important ingredient for proving later on that various statements about measurement and disturbance, and so that it all depends on this. Let me see what my plan was here. Yeah. So, so I wrote rather explicitly this commutation condition for all A. And actually there is a shorthand notation for that, which I will use in the future, and therefore this is a good place to introduce that. So, the notation for this idea that F1 commutes with a set of operators. This is to say that F1 is in the commutant of this algebra. So this prime read as commutant of. Right? So, and the commutant in general, so if S is a subset of operators, then S prime is the set of operators X, also in DLH, so that S is equal to Sx. Well, let's say Xa is equal to Ax for all A in that set. Right? So this is standard notation. It's of course due to von Neumann, who also introduced the concept. And one of the most important statements about the commutant is so S prime is always a weakly closed algebra. And so I didn't introduce the operator topologies explicitly, but that just means that an operator is a weak limit of other operators if all its expectation values converge. Let's say in arbitrary pure states, if it's a bounded sequence, then it's the same as saying that it converges for all density operators. That's also called the ultra-weak topology. And this immediately follows from this commutation condition. Right? If a sequence of operators satisfies this commutation condition, a weak limit will also automatically satisfy it. So commutants will always, and also if two operators satisfy it, then I can first pull through A and then B. So AB will also be okay. So it's an algebra. What is not so clear is, what's actually not true, is that if this holds for A, then it also holds for A star. This is usually guaranteed by applying this only to sets, or actually this is the most useful case, where the set S itself contains with every element also its adjoint. And then of course the condition, what you get out is a weakly closed star algebra. And these guys are called von Neumann algebras for good reason. And von Neumann proves the following. So if if S star, or let's say, if the set of X star, X in S, is also contained in S, then S double star is the weakly closed star algebra generated by S. So if I take all products, all linear combinations of the products, and take all weak limits I get from this set, then I do get a phenomenon algebra. And this will be the double commutant. So this is called the double commutant theorem. And this will play some role in, I mean, this notation is very useful, and this fact is extremely useful. And we will use that a lot. Now, I wonder what to do with the last 5 minutes. Let me use the last 5 minutes, first of all, for a preview. What's next, right? So what's next is, this was an abstract dilation theorem. Now, most of the time we want to apply it in the case where A is actually a complete matrix algebra, maybe even finite dimensional. Right? For this case, we already proved via the Choi isomorphism and spectral resolution of the Choi matrix, we proved this Krauss representation. And that will also come out of here with an additional bonus, namely you learn more about Krauss operators and about the degree of uniqueness of these Krauss operators. Right? It's easier to see in this setting than the setting of the Choi matrices. For finite dimensional things, this is really basically equivalent. Or these two approaches to getting the Krauss representation are equivalent. For some of the more abstract stuff, it's quite helpful to have the general Stinespring around. So I'll show next time how to get the Krauss representation out of the Stinespring, and how to get another version of the Stinespring relation, Stinespring dilation, that has something to do with implementing a channel by steps that you would definitely want to include in your set of channels. So we gave an abstract definition of what a channel is, namely a completely positive normalized map. And so we made these conditions plausible. That's the sort of thing that you would want your set of channels to satisfy. Now, there's another way to approach this question: what is a good set of channels for use in your theory? And that would be so this the axiomatic condition is sort of a condition from the outside, right? You have arbitrary maps between these B of H's, and now you say, what do they have to satisfy for this to call this a channel? There's also an approach from the inside, where you say, certain things I definitely want to be included in my set of channels. And basically, two of these things would be unitary rotations and tracing out a subsystem. And that is actually enough. So the Stinespring dilation also shows that every CP map can be implemented by adding enlarging the system, adding so-called ancilla system, and doing a unitary operation on the combined system, and then tracing out, throwing away the ancillas. So this is sort of a description from within. These should certainly be channels, and the theorem says that these characterizations are the same. It's important to get this kind of characterization because in the end we want to prove something like no-go theorems. Right? Is it possible to do a certain quantum operation? Well, what does that mean? Right? What does possible mean? Well, is there a legitimate quantum operation, a channel that will do that? And of course, so every no-go theorem explicitly refers to this domain, to this set of allowed objects. And therefore, if you want to make no-go statements of this sort, then you'd better have a crystal clear definition of channel. And the ideal situation that we have is that the description from within and the description from without match exactly. So there's no doubt of what a good definition of channel is. So these things are connected, and that will be the subject of tomorrow's lecture. And now we still have some time for questions auf Deutsch. To mark the difference. Gibt es jetzt hierzu Fragen? Okay. Wenn Ihnen welche einfallen, auch später. Also in English if you want. Okay, so see you tomorrow.